So a couple announcements to start off. I was asked about TA office hours. The TAs have agreed to hold an office hour Wednesday afternoon, like after class, in this room. So starting today, if you want to stick around for TA office hours, you can do that. We'll just have them set up, and you can answer questions. They can answer questions in here. So I've put some notes here. There's been some discussion on Piazza, which is great, about the guess temperature that should be used and computing the radiation resistance. Also been a lot of questions on the boundary conditions for the matched rate boundary. Right? There's this adiabatic boundary, and then there's a matched rate boundary. I've put that as spoilers so that you can go to office hours to get the answers to that. So. If you can stick around, again, stick around for office hours after lecture. I think they're going to talk through some of that. Are there any questions on the homework that you want to ask right now? Any other questions?
They can't be those questions.
They could be those questions. I'm not. So if you can stick around for office hours, I mean, they'll go through it in more detail than I can do in 2 minutes. Yeah. Okay. All right, so then let's finish up the discussion from last time. We were going through an example problem, our egg in a microwave. Let's finish this up real quick because we have kind of a lot to get through on the next topic, which is extended surfaces. So I'm going to kind of go through this quickly just so you can see what the answer looks like. If you have questions on it, just kind of stop me. All right, so remember what we're doing here is we have this spherical egg, as we've called it, in a microwave, and we've got radiation hitting this egg, and it's being absorbed at some rate that's position dependent. So you have G dot triple prime, this volumetric energy generation, which is given to us by R times alpha. Right? Alpha is just some constant coefficient. So last time we went through, and you maybe remember the derivation, so we went through, did the control volume analysis, and came back with an expression for temperature. All right, that expression for temperature down here is a general form of the expression. You have the C1 and C2 that appear. Those need to be solved for with boundary conditions. Right? And this is the same process that you do for any conduction problem, just as a recap. Right? You go through, get the ODE in terms of Q dot, then you have to substitute the rate equation, and then you get an ODE in temperature. Right, you solve that ODE in temperature like this, you get your general solution, and then the job is to enforce boundary conditions. So for this problem, let's think about what the boundary conditions are. Let's actually enforce them. First of all, how many are there? There should be 2, right? Because you have 2 unknown constants. So first boundary condition, BC1. So let's think about let's think about the ends of the domain. Right? So we're modeling this domain from r equals 0, right, at the center of the sphere, out to the outer diameter of the sphere, the outer radius of the sphere. So let's think about what's happening at r equals 0. Right? That's one of the boundary conditions. It's a little weird to think about because it's right in the middle of the domain, but there's a symmetry there. Right? At r equals 0, there's symmetry, and so something kind of special happening at that spot in terms of heat transfer. And that is that there's no heat transfer, right? At r equals 0, Q dot is 0. If you think about that a little bit, if everything is sort of uniform, in the situation where there's no reason why heat would flow, say, from one side of the egg to the other side, right? Everything is uniform. So the heat flow at that middle point is 0. So we'll just say Q dot at r equals 0 is equal to 0. Another way of thinking about this is that the temperature gradient has to be 0, right? So we can actually write this as dt dr at r equals 0 is equal to 0. Okay, so that's boundary condition 1. Let's state the second boundary condition, and then we'll come back to that first one. So the second boundary condition is at the outer radius, you have conduction going into that, let me maybe be a little more careful here. So you have Find a place to draw. How about down here? So you have this sphere like this. And what I'm saying is at the outer edge of this domain, that's at R equals, I guess, R out or whatever we're calling this, R out here. We want to draw an infinitely thin surface and look at what's happening as heat flows across that. So it's a little hard to see. But what I'm saying is you have heat flowing in this direction into the surface, and then you have heat flowing in this direction out of the surface. So we're matching the rate in the domain, which is conduction, to the rate on the outside of the domain, which is something else, right? It's convection, radiation. Like in your homework problem, you've actually got a lot of stuff going on. But there's still a rate equation that governs that. Okay? So the second boundary condition is a matched rate boundary condition. And let's just write out what that would be. So we're saying Q dot at R equals R out, that's conduction, is equal to, I guess in this problem we just have convection. Right, so the only thing happening is convection. H bar times AS times the temperature at R equals R out minus T infinity. So those are our two boundary conditions. Now the task is you take your general solution for temperature, which appears down on the left side there, and substitute that into those boundary condition equations to get your unknown constants. So we can do that. Let's take BC1 first, BC1. So if I substitute in my temperature expression, let me just do that. So that's d dr of minus alpha over 12k r cubed minus c1 over r plus c2. That equals 0. By the way, this is all evaluated at what? R equals 0. Okay, so let's see. I can take the derivative. I end up with, let's see, where my notes go here. So you end up with this, right? You say dt dr is actually equal to minus alpha over 4k r squared plus c1 over r squared, right? And that's, now we have to evaluate all of this at r equals 0. Fine, so there's a problem, right? So I can plug in r equals 0, that first term goes away. What about the second term? C1 over r squared. Well, C1 over 0, right? It's infinite. So how do we deal with that problem? Yeah, we cry. Yes, we cry. And then we realize that we can make our problems go away if we set C1 equal to 0. Okay? So what that's saying is C1 equals 0. It has to equal 0. If we want any kind of a solution at all, we have to have C1 as 0. It's saying, I want my solution to be defined. I want it to be a real solution, not an infinite solution. So by definition, it has to be 0. Right? That's kind of tricky, but it's true in this case. So in this situation, by substituting 0, we find that C1 has to equal 0. So we've done one of the boundary conditions. So let's look at the other boundary condition, BC2. So BC2, we already kind of started that out, but let's take Q dot at R equals R out equals H bar AS T R equals out minus T infinity and substitute in the temperature expression. So if we do that, let's see. Let's just write it here. I'm kind of short on room, but let's try this. Minus K AC dt dr at R equals R out is going to be equal to H bar AS T at R equals R out minus T infinity. So all I did is I just wrote out the conduction equation, Fourier's law, and then the Newton's law of cooling on the right-hand side. So we're matching the rates. We're matching the conduction rate with the convection rate. Or in the case of the homework, match conduction rate with the rate equation that governs what's happening outside your domain. Okay, question?
So are we assuming that there's no radiation coming from the A outward?
In this problem, yes, we're assuming no radiation, right? I'm saying only convection just for the sake of simplicity. If If you have radiation or if you have other stuff going on, you have to include that. But remember the resistance model, right? Your resistance model is a potential and a total resistance. So remember that part. Yeah?
Can you replace that first part of your second boundary condition with G dot? Is it equal or would that not be equal?
You can, except you still need to evaluate, let's see. So if you're able to compute G dot, you could, right? If you're able to compute G dot, you could do that. In this case, we're doing a surface balance, which is just looking locally like what's happening at the surface. But yeah, if you know the total generation, you could also do that. Yeah. I'd like you to follow this approach for now, just because there are many cases where you can't like anticipate what's going to happen. But yeah, that makes sense. Okay, so we've got this. Now we need to substitute in our equation for temperature, which we can do. I'm just going to kind of show you the simplified result here. So on the left, we take the derivative of this temperature equation here and plug that in, and we get K times alpha over 4K times R out squared is equal to H bar times the quantity minus alpha over 12K R out cubed plus C2 plus T, or sorry, minus T infinity. Okay, so at this point, you can maybe see where this is going. So we have this equation, right, this equation here. We have one unknown left, C2. Everything else is known. We've evaluated this equation at R out. So there's no remaining unknowns except for this constant. So just solve this equation for C2, and you're done. Right? C1 is 0, C2 is this equation solved, and then that gives you your expression. Okay? So that's the example. Other questions on this? Yeah? When would the areas not cancel? So when you're looking at a boundary condition and say like spherical coordinates or cylindrical coordinates, the conduction area at that boundary is always going to be equal to the convection or radiation area because it's at the boundary, right? It's infinitely thin. So they should, in the boundary condition, always cancel, right? It's just when you're deriving the expression for temperature that they're not equal.